Welcome to Eager Space. I've always said that astronauts are very good sports. The Apollo astronauts spent 3 days crammed into a tiny capsule on their way to the moon, and another 3 days on the way back. Not much room and not much protection from the hazards of space, such as radiation. The current Artemis program's Orion capsule is roomier, but it's still fairly small and cramped. What would you want for your trip to the moon? A bare-bones capsule, or something more like a space bus with more room and more amenities? Big spacecraft are of course very expensive, so what you would need is a reusable space bus. That is the point of the cycler architectures, invented, or at least formalized in 1985, by this guy that you might have heard of. Here's the basic idea. You launch your bus into an elliptical orbit that goes around the Earth and out to the moon. You launch from the ground to meet up with the bus when it's near Earth, and then you stay on the bus until you get close to the moon, and you hop off and land on the moon using a short-ranged lander. The return trip is pretty much the same, except you likely hop on when the bus is heading home rather than when it's heading out. That sounds great. You get a nicer environment for your trip, and you can bring along new modules to expand your living space each trip. Over time, you can build what Aldrin called a space castle. These orbits are stable enough that the bus only requires a little propellant to stay in the orbit. There are a few issues. The first is the size of the bus. The Apollo spacecraft massed about 45 tons. And to send that to the moon required a launch vehicle about 2,800 tons. If we assume our bus is 200 tons, then we need a rocket 4 times the size of the Saturn V. You might get twice the performance with a fully expended Starship, but if you want to go bigger, you really need a refueled Starship. This is one of the reasons that lunar cyclers haven't gotten much interest. A vehicle that takes 2 to 4 Saturn Vs to launch hasn't been practical or affordable. A second issue is related to the biggest misconception about cyclers. They do not take you from Earth orbit to lunar orbit, or vice versa. The bus does not orbit either body, it flies by them. From the Earth's surface, or low Earth orbit, you need to chase after the bus to catch it. The bus is traveling roughly the speed that it takes any spacecraft to get to the moon, perhaps a little faster. You then ride the bus to the moon, but instead of just barely reaching the moon so you can easily get into orbit, the cycler has some velocity as it goes, and you therefore need some extra propellant to get into orbit. That means the energy to get to the moon using a cycler is roughly the same as it would take if you followed the Apollo approach. You just get to stay in a nicer room for the trip. So why bother? Well, the hope is that instead of using a high-performance and very expensive lunar ship, you could instead use some sort of space taxi to get you to the cycler, and then from the cycler to the moon. The space taxi doesn't have to support you the whole time, and therefore it can be cheaper and simpler, and that might make the overall system cheaper in the long run. The orbital mechanics is more complex than I showed. We set up the orbit of our bus so that it goes out to the moon and loops around it to drop people and cargo off, and then it returns back to Earth. After going around the Earth, it takes the same trip over and over. But the moon isn't just stagnant in space, it is orbiting the Earth. And by the time our bus is leaving the Earth again, the moon is rotated around the Earth, so it's not anywhere near the orbit of our bus. That means our next bus trip doesn't go anywhere useful. It just goes out to around the lunar orbit distance, then comes back. Then the next trip the moon has continued its orbit, but still isn't close to the original position. And then finally, if we set up our orbits properly, the moon returns to the original position relative to the bus orbit, and we can visit again. A cycler therefore has limited travel opportunities. This chart shows the times. The bus gets to visit the moon roughly every 26 days, with 2 trips to nowhere in between the lunar visits. This shows that the lunar cycler will get you to the moon, and then you need to wait nearly a month before it swings by to take you home. Like a bus, it gets you where you want to go, but the timing may not be as convenient as you hoped. One can, of course, launch as many of these cyclers as you want in different orbits, and there are other possible lunar cycler orbits that might be used. For the moon, I think cyclers only start getting interesting when you have moved beyond the lunar base to a settlement or a colony. In those scenarios, dedicated Earth to Cycler spacecraft and Cycler to Moon spacecraft makes sense. We are, of course, a long way from that right now. But it's Mars cyclers that are more interesting. To understand them, we need to understand a bit about orbital dynamics. The Earth and Mars both orbit the Sun, with an orbit of the Earth taking a year and an orbit of Mars taking about 1.9 years. When the planets are at their closest point to each other, it's known as conjunction. Because the Earth orbits more quickly, it will get ahead of Mars until they are opposite each other, a position known as opposition. Eventually, the Earth will catch up at the next conjunction, about 26 months after the first one. This cadence shows up in science missions. Roughly every 26 months, there is an opportunity for a new mission to head to Mars. It is possible to travel to Mars at other times, but it's much more expensive in terms of propellant use, and that means a heavy payload penalty. Saying it's at conjunction isn't precisely true. Heading from the Earth to Mars, we launch at about 44 degrees before conjunction for the most energy-efficient transfer, with the Mars encounter happening after conjunction. Our spacecraft will chase after Mars and eventually catch up with it because it's traveling faster than Mars. Coming back from Mars, we need to launch when Earth is roughly 75 degrees behind Mars so that we can get to Earth orbit when the faster Earth gets there. In both cases, the journey will take 200 to 250 days if we choose the most energy-efficient trajectory. If we're willing to choose a less energy-efficient trajectory, we can get there more quickly, say 175 days. But we end up with less payload because of the extra energy required to do the transfer more quickly. The Mars cycler has an orbit that dips inside of Earth's orbit and travels beyond Mars' orbit. The orbital path is chosen so the orbital period is the same as the time between conjunctions. So we know that every cycle we can launch from Earth to meet the cycler at point A, and then hop off when the cycler and Mars reach point B. The cycler travels quickly, and you get there in about 146 days, about 17% faster. There is, of course, no free launch. You need to catch up with the cycler, and it's going faster than the Earth. And that typically requires 40% more delta V to perform the catch, which means you need a more capable vehicle. You also arrive at Mars with more speed that you will need to get rid of to go into orbit or land. Coming back, you hop on the cycler when Mars is at point D and hop off when you reach the Earth at point D. But that doesn't actually work. Remember that we only get the proper alignment between the cycler and planets every 26 months. That means that the cycler isn't there when Mars gets to point C. For the return journey, your only choice is to spend a full cycle, 780 days on Mars, and then hop on the next cycler at point B, and then spend 633 days waiting for the next encounter at point A. That's 21 months, most of it spent in interplanetary space while beyond the orbit of Mars. This cycler is optimized to reduce the time spent on traveling from the Earth to Mars, but using it to come home is a very slow trip. What we need is a second cycler built to optimize the travel time from Mars to Earth. It crosses the path of Mars at point C, then the path of Earth at point D. With the second cycler, we can do that trip home in the same 146 days. Aldrin called these two cyclers the up escalator and the down escalator. I said that chasing the cyclers required 40% more delta V than a direct trip to Mars. How does that affect our mission architecture? It helps to look at an example, and I've chosen the Apollo Command and Service Module. We can calculate the delta V of a spacecraft using the rocket equation, which says we take the specific impulse of the engine, multiply it by 9.8, and multiply it by the natural log of the initial mass of the vehicle divided by the final mass when we've used all of our propellant. If you want more information, see my video, The Care and Feeding of the Rocket Equation. Plug the numbers in for the Apollo Command and Service Module, and we get about 3,150 meters per second of delta V. That's surprisingly close to the 3,600 meters per second it takes to get to Mars. This is a good sort of vehicle for us to use as a taxi. And since I know somebody is wondering why didn't I choose the much newer and more modern Orion capsule, the Orion capsule is a bit of a pig that has close to twice the mass of the Apollo capsule, and the service module doesn't carry much fuel. Plug Orion's number into the rocket equation, and we get about 1150 meters per second of delta V. Not even close to what we need. To compare the direct trip to the cycler, I'll start by modifying the Apollo command and service module to generate enough delta V to get to Mars. That bumps us up to a 34-ton vehicle with 24 tons of propellant. The Aldrin cycler takes about 5,000 meters per second of delta V from low Earth orbit. We will need to modify our vehicle quite a bit to get there. We will need 63 tons of fuel carried in a bigger and heavier vehicle for a total mass of about 75 tons. It might look a little like this. To get 40% more delta V required a little more than twice the vehicle mass. The idea of a cycler is to use a small and simple taxi. But the high delta V requirements means a big and heavy taxi, plus a big rocket to launch it. And remember that there is a separate launch or two to get the cyclers into their orbits. The Aldrin cycler orbit is designed to do one orbit every cycle. There are many other cyclers that relax that requirement. Here's one that cuts the travel time down to only 75 days, which is very quick. The downsides are that it requires 120% more delta V to catch it as it goes by Earth, and it has about 30% more velocity at Mars. Oh, and it only shows up every 5 cycles, or every 10.7 years. But it does get there really quickly. If you're shipping cargo, there's an interesting slow boat option. The cycler known as 6S9 takes 200 days to get from the Earth to Mars, and repeats once every 12.8 years, but it requires very little delta V to get to Mars. Pretty much the same as the non-cycler version, so it's cheap. If you want to send cargo back and forth, maybe you choose this cycler. The taxi approach and docking architecture has some unfortunate failure modes. Because you have to catch the cycler, there's an instantaneous launch window. If you have to abort, the only option is to wait for the next cycler, which takes 26 months unless there are multiple outbound cyclers. Direct-to-Mars approaches have a 20 to 30 day window, so there's a lot more flexibility there. If you rendezvous with the cycler but can't dock, you are stuck in your taxi for the whole trip to Mars. You maybe brought enough food with you, but you may not have the equipment to provide breathable air and water for that long. You also don't have exercise equipment or good radiation shielding. You will be spending the full 146 days in your taxi. If you have propulsion issues and can't even meet the cycle, you're stuck in your taxi and you aren't getting near Mars. You might end up back at Earth in months or years depending on the failure. The probability of your survival is not high. In addition, electric propulsion isn't practical. The time between departure and meeting the cycler requires on quickly being able to match the cycler's speed, and current ion engines can't generate enough thrust to do that. They could slowly spiral out to reach the orbit of the cycler, but that will take months and therefore does not work for crewed flight. These scenarios are major issues. In summary, cyclers get you to Mars more quickly. But big cycler spacecraft are going to be very expensive to design and build, and you won't build very many of them, so they won't get much cheaper. The delta V requirements for the taxi vehicle are problematic. It's much harder to get to the cycler than going straight to Mars, and the inability to use electric propulsion limits the architectural options. The failure modes are inconvenient and troubling. I'll leave you with this quote from a 1990 NASA overview of Mars transportation options. Here's what they said about cyclers. Cyclers do not appear to have enough advantage over simple conjunction all-propulsive or aerobraking to merit their need for infrastructure prepositioning, operational complexity, and give up of abort modes. If massive galactic cosmic ray shielding is needed for Mars transfer habitats, the cyclers may show significant advantage. This point needs further evaluation. And that's all for cyclers. Today's song is Stuck in a Loop by Devo, off their 1990 album, Smooth Noodle Maps.